Hello everyone, welcome to our presentation on JShrink, in-depth investigation into debloating modern Java applications. This research is completely open access and a copy of the paper is provided at the link on this slide if you wish to view the research we've carried out in greater detail. This research was carried out by me, Bobby Bruce, Tianyi Zhang, Jaspreet Arora, Harry Zhu, and Miryung Kim. Let's start with the motivation for this research. It can be summed up in a four-word sentence. Modern software is bloated. Let's talk about what we mean by this. This is the typical model for software. Users want a feature, so they obtain an app that has this feature. Though app developers have different motivations and will provide other features in this application. And this results in the application being bigger than it actually needs to be. This problem exists further down the line. The app developers require libraries for desired features within the library, but those library developers will provide other features that are not immediately needed for the task at hand. You can extend this outwards. Libraries depend on other libraries that depend on other libraries that depend on other libraries, most of which are probably going to have features that are simply just not needed. So these libraries are larger than they need to be. This problem means more storage is needed, increases the download times, and increases the attack surfaces. If you want an example of how an attack surface may be exploited through bloat, please look up a gadget chain attack. The motivation for our work is to get rid of code that is not needed. That is bloat, with the end goal of reducing the total size of the program and the library dependencies. Previous work. There's been lots of good work on debloating C and C++, but Java has largely been ignored. There's one exception to this, and that is Tip et al.'s UPSLA 99 work. In this work, they proposed and evaluated a set of Java bytecode transformations, and these transformations have been utilized heavily by other research in this area. Though we found, upon surveying the literature, the effectiveness of these transformations at preserving program behavior has not been evaluated thoroughly in a modern Java context. And what do we mean by that precisely? Well, in short, previous works relied purely on static analysis. Yet, Java contains a lot of dynamic features. What do we mean by dynamic features? Well, I'll provide here a simple example of a program that utilizes the reflection API, which is what we classify as a Java dynamic feature. Please take time to pause the video and fully understand this program. The key lines of interest are 13, 14, and 15, where an argument is taken to invoke a method using the Java reflection API. This argument is specified at the command line level when executing the program. Here's a question. What methods are reachable in this program? What we mean by reachable is what methods can ultimately be executed when running this program. I think you can all say that technically they're all reachable. And when it comes to debloating, this answer is true, but unhelpful. Essentially, if we're looking to debloat this program, we need to understand how it is used and what is ultimately called from line 15. So to do practical reach analysis, we require a dynamic component. We require running of the program to see how ultimately these dynamic features call other methods in the program. Without decent reachability analysis, debloating is often simply impossible, especially for Java applications of a non-trivial nature. They will inevitably contain dynamic features. Our solution to this problem is JShrink, and here we provide a high-level overview of JShrink. JShrink starts by inputting Java bytecode, and then creates what we call the extended call graph. The extended call graph is like an ordinary static call graph, but extended to account for the dynamic calling within Java. The dynamic analysis component is carried out by our component, which we call JMtrace, which we'll talk about in another slide. The static analysis is carried out by the third-party Suit library. Once we obtain our extended call graph, we can begin applying bytecode transformations to the code, with the goal of outputting Java bytecode that is debloated in comparison to the original input. Let's start with understanding the extended call graph using a basic example. Please consider the program on the left. Again, please feel free to pause this video so you can fully understand this program. It is much like what we saw before, except this time the reflection API is used on a static constant string, foo, and the method bar is called. The call graph analysis starts by obtaining all the methods in the program. And then static call graph analysis is used using the Suit library. Using static analysis, we can only determine this: main calls bar and foo calls foo called. Therefore, if we were to carry out debloating at this level, we would probably debloat this, as foo and foo called and foo bar all appear to be unreachable if only using static analysis. This would simply not work. Upon running such a program, you would receive a method not found error, as foo is actually called. It's simply just called through a dynamic feature, the reflection API. Therefore, we introduce a dynamic component. We run the application and see which methods are called and extend our call graph accordingly. So we figure out that main does actually call foo, and that gives us a more complete call graph. And from this call graph, we know we have to keep foo and foo called within the program. Though, statically and dynamically, foo bar is never called, and therefore we can safely remove foo bar from the program. Our dynamic analysis is carried out by JMtrace. JMtrace is a JVM plugin that records all the methods executed in a particular run. Using this information, we can begin applying transformations at the Java bytecode level. We start with the call graph that we built using JMtrace and Suit. As shown in the previous slide, we can easily determine the unused methods and then carry out unused method removal. From the call graph analysis, we can also determine methods that are inlineable and therefore inline methods. A method that is inlineable is one that is called only at one location in the program and therefore may be inlined to that location and the old method removed. Using the call graph analysis and some features provided by Suit, we can determine the unused fields and then use unused field removal. By knowing the unused methods, we can determine the unused classes. An unused class is a class that has methods in it that are never used. Suit can give us class hierarchy information, and with these two, we can use class collapsing. What we mean by class collapsing is two classes, one a subclass of another, may be merged into a single class. This reduces the bytecode as there is an overhead in creating classes in Java bytecode. Following slides, we're going to give some basic examples of how these work. Consider the program on the left. Method 3 is never used, and therefore it can be removed from the program. This is unused method removal. Unused field removal. The field bar is never used, and therefore can be removed from the program. Method inlining is a little more complex, though I hope it's easy enough to understand. Method 1 and method 2 are only called from one location in the program. The main method, method 1 in the print statement and method 2 in a print statement. They are inlineable at this location, and therefore we inline them and remove the old methods. Method calls have a bytecode overhead and therefore worth removing if possible. Class collapsing is slightly more complex, so please feel free to pause the video so you understand what's going on here. There are three classes, A, B, and C. C is never used and therefore can be removed from the program. Having A and B is redundant in this case. Therefore, we may merge A into B, so we only have the remaining A method, A class. It's worth here talking about checkpointing, which is another addition to JShrink. Checkpointing is our way of making JShrink safe. Checkpointing works by first checkpointing the application that's being transformed before applying the transformation. We then apply transformation, run the application's tests, and if these tests pass, checkpoint again and apply another transformation. If any of the tests fail, we restore to the checkpoint. If you think this through, you can see this ensures safety modulo the application's test suite. We consider this costly but safe. It's costly as you have to run the application's test suite every single time you apply a transformation. In order to evaluate JShrink, we came up with the following research agenda. Reduction. How much Java bytecode reduction is achievable when applying different transformations? Preservation and robustness. To what extent are program semantics preserved when debloating when using JShrink? And finally, what is the impact of using the dynamic analysis compared to a completely static approach? First, we obtained some candidate programs. Our slashing criteria was as followed. They had to be popular. As we were surveying GitHub, we considered this to have at least 100 GitHub stars. They had to be compilable. They had to time out and accept. We had a 10-hour timeout for the static analysis. Therefore, they had to meet this timeout criteria. And they had to be testable. They had to come with a JUnit test suite. We obtained 26 applications, which are displayed here, with an average lines of code of just under 15,000, though there's a wide distribution within this set. Our first research agenda, reduction, we found that the method removal transformation applies the greatest reduction at 11%. Then method inlining followed by field removal. Class collapsing achieves 0.1%, which is rather low and disappointing considering the engineering complexity of that transformation. Applying all the transformations without checkpointing, we achieve a 14.2% reduction across the set, and with checkpointing a 13.3% reduction, thus showing there is a cost in applying checkpointing. Preservation and robustness. We held back 20% of each project's tests and used the remaining 80% for the dynamic analysis. JShrink, when utilizing all transformations without checkpointing, results in 81 test cases of the 5,213 failing, or 1.6%. Upon further analysis, we found that almost all these were due to the class collapser. And all known bugs were due to limitations in the suit static analysis, simply not giving us information we need to account for all cases. Interestingly, checkpointing worked exactly as we intended, with no bugs. No tests failed when checkpointing is enabled, even in the held out tests. The impact of our dynamic analysis cannot be overstated. When we turn the dynamic analysis off, that is, we only use static call graph analysis, 58.4% of all the tests failed. Remember, this is compared to 1.6% with dynamic analysis, and 0% if checkpointing is enabled. Most failures in static analysis were due to JVM validation errors, no class def found errors, and class not found exception errors. The discussion points for this work we think are as follows. We evaluated tip-of-alls transformations and found that method removal is the most effective transformation, though they all reduce bloat. Class collapsing is the least effective, the most difficult to engineer and the most error prone, so perhaps this can be dropped. Reachability analysis also simply requires a dynamic component. Using a purely static analysis is simply not going to work. We also wish to note here that dynamic analysis is only as good as the test inputs, and this does put some onus on developers to produce good test suites, though we suspect tests may be automatically generated if required. Thank you very much for listening to our presentation. We hope to have some interesting questions at this year's FSC.